Binary search. It's an extremely important concept to understand as a programmer and often comes up on technical interviews. What happens is you'll often come up on a problem that goes something like this. You have an array of sorted elements and you need to find the index of a certain value. Like maybe you have a collection of customers retrieved from a database and need to find a customer with a specific name. That sounds pretty easy, and the obvious solution is to create a function that takes the array of elements and the target, then loops over the array until it finds the target with the matching value. So just loop over the array until you find what you're looking for. The problem though is it's not very efficient. Like imagine a database with 10 million records in it and you're looking for a customer with the name of Zed. You'd have to loop over millions of records just to get there. When talking about algorithm complexity, this would be O of n, which means the worst possible amount of time it will take is equal to the amount of elements in the array. In the real world, it may not be acceptable to just loop over a giant array. Binary search offers a more efficient approach. The best way to think about it is searching for something in a dictionary. If you're looking for something in the J's, you wouldn't start at A and flip through every page to get there. Instead, you would open it up in the middle, and if you overshoot to M, then you go backwards until you find J. Or if you undershoot to H, then you would flip forwards until you find J. And that's exactly how you do a binary search. So let's go ahead and implement it in code. We'll start with a function called search that takes the array and target as inputs. Now we'll also add arguments for start and end that define the search area of the array. Notice how I'm using an equal sign here to set default values for these arguments, because when the function is first called, we'll want to search over the entire array. So we start at index 0 and end at the last index, which is the length -1. Now that we have this information, we can create a conditional that says if the start is greater than the end, then we know that the value has not been found. That means it searched through the entire array without finding the target value, in which case we can return -1. Now the most important aspect of this algorithm is that we find the middle element of the array. We can set a variable up for that adds the starting point to the ending point and divides by 2. We also wrap this in math.floor to ensure that it returns an integer instead of a decimal value, which would make no sense for an indexed array. Now at this point, there are 3 different things that can happen, and I'm going to set up conditionals for each one of them. The middle index can equal the target, the middle index can be greater than the target, or the middle index can be less than the target. If the middle index equals the target, that means we found the value we're looking for, in which case we can just return that index. However, if the middle is greater than the target, then we know that we overshot on the search. To continue searching, we'll make this a recursive function by calling the search function again, passing it the array and target along with the same start value, but we'll change the ending value to the element adjacent to the current middle value. This has the effect of slicing the search area in half. If this array is 10 million elements long, we just reduce the required iterations down to 5 million. Now the other condition, when the middle is less than the target, we will also recurse using the search function, but this time we'll change the starting value to the middle value +1. That also slices the array in half, but does so on the other side because we know the target element must be there. Congratulations, you just implemented a binary search. Go ahead and create a sorted array with some strings and then call the function to inspect it. It should return the element you're looking for, or -1 if it's not found.